Let's consider when the variances are unequal. So suppose my prior probability my likelihoods look like this. So here's my height. That's x, the x variable. And suppose my males, I have some really wide distribution in the height of the males. I have some really short males and some really tall males. On the other hand, the females go like this. So I have much lower variance in the females as compared to the males. So what I'm plotting here is P of x all right. So okay. So what is the marginal probability? What does P of x look like? So suppose that again my prior probability is 0.5, so they're equally likelihood. So I multiply these guys by 0.5 and I add them up. And of course what I'm going to get is a long tail. All right. So you notice that if you look at this function, I have two decision boundaries now. Because if my height is bigger than this number here, I'm going to say that it's going to be a male, and if the height is less than this number, I'm going to say it's going to be a male. Only in between I'm going to say it's going to be a female. So if I divide, so I'm now going to plot for you P of the probability of y is equal to male given x. It's going to look like this. This is the probability of y of 1 given x, and the probability of being female given x is going to look like this. So all I'm doing is plotting the posterior probability. Yeah.
Question about the decision.
Yeah.
So it seems like graphically in the plot gives us like the equality between like P multiplied through equality between probability of x given y equals 0 and probability of x given y equals 1. But what is the multiplying by probability of y equals 0?
The prior probability. What does that do?
1. Yeah.
Yeah. If the priors are unequal, then the two get weighted by different numbers. So if the prior probability of y is equal to 1 is large, say you have 90% chance that what you're looking at is a male, then what that means is that this thing gets pushed up, this gets pushed down. Because this gets multiplied by the prior probability before it gets divided by the P of x, the marginal. So what the prior probability does is that it can increase the weight of this before you add it to this. It's like multiplying it. It multiplies it by something, and then it pushes down this guy if they're unequal. So what it does is that it then makes this. If my prior probability is large for P of x given y1, then what that does is that it makes my decision boundary come in, because it's pushing up the blue line. All right. So uncertainty of my classifier. So this is my posterior probabilities. So I can tell you that how probable it is that I'm in class 1 or I'm at class 0 based on this posterior probability. But what about my uncertainty? So what I want to know is basically what's the variance associated with my estimate given x. So this is the probability of it, but what about the variance? And to give you intuition, you sort of would guess that my uncertainty is going to be highest right around my decision boundary. So basically right around the place where the two probabilities are close to each other, that's going to be the place where I'm most uncertain. And then as I get closer to the edges, that's going to be the place where I'm most certain. So what I want to show you is how to compute that posterior that variance. That's your uncertainty about your classifier. And here's how we're going to do it. So and let me show you what I mean by that. So I have a probability of y being equal to class I given x. That's why I just showed you how to compute it. And you know that probability, I can do it like this, and I get a distribution p of y given x, which is going to be equal to two things. It's going to have, this distribution is going to have two numbers. It's going to have a probability at y is equal to 1 given x, and a probability at y is equal to 0 given x. So that's what a distribution is. Okay, so what is the variance of my of this distribution? So I have an expected value of y given x, which is the probability of y is equal to 1 given x times 1 plus the probability of y is equal to 0 given x times 0. And you know, this is going to be equal to just the probability of y is equal to 1 given x. That's the mean of my distribution. And then we have the expected value of y squared given x. That's going to be also equal to this. So the variance of my y given x is going to be equal to the probability of y is equal to 1 given x minus the probability of y is equal to 1 given x quantity squared. So if I were to plot this relationship, if I were to plot this number, probability of y being equal to 1 given x minus its value squared for these two things that I showed you here. So let's plot it for here. So I'm going to plot the variance of y given x, which is equal to this quantity, probability of y equal 1 given x minus the probability of y equal 1 given x squared. I'm going to plot that as a function of x. What I'm going to see is that this function looks like this, where that's the decision boundary. It's going to have a maximum value right at the decision boundary. If I do it here, if I plot probability of y equal 1 given x minus the probability of y equal 1 given x squared, it's going to look like this. My uncertainty is going to be greatest right here. And that's basically the variance of y given x. That's my uncertainty about my classification. All right.